Hello everyone, I'm Michael Liu. In this video, I would like to introduce our paper, What It Wants Me to Say, Bridging the Abstraction Gap Between End-User Programmers and Code-Generating Large Language Models. Code-generating large language models have proven to be helpful for developers, as they can follow natural language, or NL prompts, and automatically generate the appropriate code. However, can end users also take advantage of it, especially given the fact that they don't write code? For example, only a small portion of the infinite space of natural language queries is effective at guiding code generation. For non-expert end-user programmers, learning this is the challenge of abstraction matching, meaning that it is often hard for them to figure out a way to express their intent in natural language that would be reliably and also effectively translated into code by an LLM, which often involves specifying the utterance at a level of granularity and detail that matches the set of actions that the LLM can take, as well as selecting suitable words, grammar, and maybe in-context examples. So, how can we help end users express their intent in natural language in a way that can be reliably and also effectively translated into code by an LLM? To address this problem, we explore the idea of grounded abstraction matching, where we map the user's natural language query, aka their intent, to a system action, and then map it back to a naturalistic utterance that is an editable example of how to consistently invoke the same system action. This gives a grounded example of the level of abstraction at which the system expresses its solutions. In this paper, we explore the grounded abstraction matching in the context of end-user data wrangling, where users are presented with a spreadsheet and are tasked with transforming or organizing data based on some analysis goal. Their job is to express their intent via natural language queries to the system. This is actually a fairly common feature in many commercial softwares. For example, Analyze Data feature in Excel or Natural Language QA in Power BI. The difference here is that we're replacing traditional code synthesis techniques with a code-generating LLM called Codex. So for example, based on this sheet of astronauts, the total number of hours they've been in space, and a comma-separated list of missions that they have flown, I wanted to ask the system to calculate the average mission length for each astronaut, and I expect to get a new column called average mission length from the system. Here, what actually happened was the LLM uses the data and user's natural language query as a prompt and generates code for this intended task, in this case a piece of Python code, and the spreadsheet will execute the code to get the final results. In this case, notice that there's an error in one of the cells, sorry Buzz Aldrin, but we'll get to that shortly. However, if a typical end user uses natural language instructions for data analysis, it usually means that they don't know Python or any kind of programming language for that matter, so we obviously are hiding the code generation part from them. Therefore, what an end user thinks happened is they write some natural language commands and the spreadsheet directly reacts with calculated results. But since they don't have access to the code, it would be very hard for them to find the source of this bug. In this case, the LLM incorrectly tried to count the number of missions by counting the number of STS, namely the space shuttle launches, but it's clear from the table that Buzz Aldrin hasn't flown on any of the space shuttle launches that would have STS in its mission name, and therefore it's running into a divide by zero error. And more importantly, it's also hard for them to improve their NL queries so that they can get the system to generate more desirable results. So that's where our grounded abstraction matching approach comes in, where instead of showing end users unreadable code, we translate and break down the code into natural language as an editable example query so that end users can read, understand, edit, learn, and also adapt based on those examples. Let's see this pattern in action in a prototype Excel add-in. So this is the interface. We have the spreadsheet data on the left, and our system sits in the sidebar on the right. To start, I can simply type in my query in the query box at the top and hit Go. It'll take a few seconds to process the request. Under the hood, the system translates the spreadsheet data into a Python pandas data frame and append the user query as a Python comment and send these as a prompt for the OpenAI Codex API to generate code. And here's what it's giving me back, a piece of generated Python code as well as the execution results by our Excel add-in that's appended to the original datasheet. Notice that the code should be hidden from end users in real cases. We're showing it here so that we can have a better idea of what's going on. In the meantime, we also generate the new natural language grounded utterance based on the Python code and display them in the How the System Solved the Task section in a series of editable text boxes. Although the user won't be able to see the actual code that produced the results, they would be able to leverage this grounded utterance to understand what the system did and how to talk to the system to fix any potential issues if necessary. So for example, the user would be able to figure out that the system was counting the number of missions by counting the number of occurrences of the word STS, which is wrong. And the correct way to do it, based on the data, would be to count the number of commas and +1. And after editing, the users can click the Update and Go button to see the updated grounded utterance as the new query for the autonym, which in this round generates the correct code and result. As in another example, this is a spreadsheet containing the results of a list of Super Bowl games in the past. Let's say a user would like to figure out how many Super Bowls the city of New Orleans has won. And they can just type the query in and see what the system comes up with. Now the result that the system generated 3, but it looks like the New Orleans only appeared once in the winner column. By examining the grounded utterance, the user would be able to figure out that the system was looking at the wrong input column, host city here. One lesson that the user immediately learned is that the query should be more specific in terms of which input column should be used to calculate the result. So he changes host city to winner and is to contains, and then rerun it through the system, which would give us the correct result, which is 1. So that was a demo of how the system works, and the core thing that enables this demo is the automated translation and breakdown from code to natural language grounded utterance. In a nutshell, we took advantage of the fact that code has syntax structures and use abstract syntax trees of the generated code to reverse engineer the commands. So in this case, the code is a fairly simple Python statement, and we iteratively parse and break it down into subtrees and translate each part of the end node into natural language and then concatenate them together at the end. And an important assumption that we have is that the breakdown should be able to generate the equivalent output as the original query. In reality, on our custom datasets, as well as the user study data, this is true about 86% of the time, which we thought was sufficient for us to explore the effectiveness of our approach. We have also designed an alternative ungrounded version of the add-in. It essentially guides users towards reframing their original query using best practices of prompting LLMs established by prior work, including decomposing the task into smaller and simpler problems that LLMs would be better at handling, specifying the shape and type of the output, in this case a new column of characters or words, and avoiding relying on background information that is not present in the data. To compare the two versions, we conducted a between subjects study with 24 participants with varying levels of prior programming experience. Participants were asked to use natural language to query the system, where the system would generate some results and grounded utterance, from which participants would know how and why the system failed if it did in a grounded case, and then edit and improve their queries, either based on a grounded utterance or by themselves, using some rewrite strategies that are based on their mental models of the system. Please check out our paper for detailed taxonomy and a qualitative and quantitative analysis of the failure modes, as well as the rewrite strategies. In particular, as a result of the grounded utterance, end users were better able to understand what the system was doing under the hood and verify if the system did was correct or not, and be able to isolate the bug. Indeed, participants found the breakdowns made LLMs more tractable, for example. This user said, it helps me understand what's going on, and therefore whether the result is going to be accurate or not. The more you use the grounded utterances, the more confident you'll get to their values, and you get less worried. In addition, users are able to improve the LLM generation in a lightweight way by just editing the grounded utterance, and ask the system to do another round of generation, and then get an updated result. And participants thought that the grounded utterance was very programmable, and it provided opportunities for you to modify and iterate over it. And perhaps most importantly, working with LLMs require users to use queries LLMs can operate at. But learning this level of abstraction is usually pretty hard. But with our grounded abstraction matching approach, users can self-adapt to more effective query distributions. So for example, after seeing the model failed at the previous query, users would form the mental model of, I need to specify the column that I want the system to look at, and use that strategy in their following queries. For example, a user reflected that I can see what it's working with, and then I can kind of shift my understanding of what it wants me to say. So in other words, this implicit learning process helps end users generalize to novel data sources and also interactions. And thank you for watching the video. For more details on the system and the user study, please read our paper.